Welcome to our podcast, where we explore the fascinating world of data structures. Today, we're diving into an innovative solution that can revolutionize how we handle dynamic arrays, the shift-to-middle array. Now, if you're scratching your head looking for a new approach to optimize insertions and deletions, you're in for a treat. The shift-to-middle array is designed specifically to enhance performance compared to traditional structures like deques, vector, and linked lists. So what sets it apart? Here are some of its standout features. 1. Amortized O1 insertions and deletions. Yep, you heard that right. You can insert or delete elements at both ends in constant time on average. This is a game changer for applications requiring real-time modifications. 2. Random access in O1. Unlike linked lists that can be slow to access, this structure allows for quick retrieval of any indexed element, maintaining the speed you need. 3. Improved cache locality. This is all about keeping your data close together in memory, which is a boon for performance. Better cache locality means your CPU can access data faster, reducing wait times. 4. Support for parallel processing. We live in a multi-core world, and this array is built to take advantage of that, equipped with SIMD, single instruction, multiple data optimizations for even more efficiency. But how does this all work? Well, unlike deques, which relies on fragmented blocks of memory that can lead to performance bottlenecks, the shift-to-middle array actively redistributes space as elements are added or removed. It cleverly shifts elements towards the middle, minimizing the need for costly memory operations. Now let's talk numbers. Here's a quick comparison with some common data structures. Accessing an element by index is fast, O1, for both the shift-to-middle array and standard arrays, but linked lists take ON. Inserting at the head, ON for arrays, O1 for linked lists, and just O1 amortized for our array. That's pretty impressive. Oh, and just to give you a flavor of real-world performance, benchmarks have shown that this structure really shines when you harness modern CPU capabilities. So if you're running complex applications or dealing with lots of real-time data, think about giving it a try. When should you consider using the shift-to-middle array? Well, it's perfect for high-performance queue structures, game engines, networking tasks like packet buffering, and even for handling dynamic sequences like computational geometry and physics. The great thing is, if you're itching to implement it, you can easily include it in your project with just a line of code. No fuss. As for where to find more information, you'll find full documentation and performance benchmarks in the project wiki. Plus, it's open source, so contributions are welcome. Before I wrap up, think about this. How much more efficiently could your projects run if you opted for a structure designed specifically with modern demands in mind? It's exciting to think about the possibilities. Thanks for tuning in to this deep dive on the shift-to-middle array. We hope you found it enlightening and maybe even inspiring for your next project. Until next time, keep exploring the incredible world of data structures.